Page 8 of Chapter 16, Complex Numbers and Eulers for MHL. Number 4, use the principle of math induction to prove that arg of z of n is equal to n arg of z for all n that are positive integers. Okay, so remember math induction. So the first step of math induction is to look at P1. The first step of math induction is to say what our Pn is, right? So our Pn is that the arg of z to the n is equal to n times the arg of z for all n that is a positive integer. Okay. Then we're going to look at P1. So P1 says, oops, that was a terrible job. Okay. So P1 says that arg of z to the 1 is equal to, and that's the left-hand side. The right-hand side says 1 times the arg of z. And yeah, arg of z to the 1 is equal to arg of z. And 1 times arg of z is also equal to arg of z. So P1, thus P1 is true. Okay, this is the case of n equals 1. Now let's look at the case of pk. Okay, so assume that p of k is true. If we assume that p of k is true, then we know that arg of z to the k is equal to k times arg of z. Now we're going to look at the left side in terms of k plus 1. So if we know that, or if we are starting with the argument of z to the k plus 1, let's try to massage that until we get this expression on the left side. Well, that's pretty easy to do with the exponent. We just separate it into z to the k times z to the 1. And then we know that the argument of two things that are multiplied together is equal to the argument of the first plus the argument of the second. And the argument of z to the k, we already know, is k arg z, because we assume this is true. And the argument of z is just argument of z. Argument of z could be written as 1 argument z, right? And if I have k argument z plus 1 argument z, isn't that the same as k plus 1 argument of z? And if that's true, then I have proven it, because I started out with arg z to the k plus 1, and I finished with k plus 1z. You can see that basically that is the same thing as this, except for instead of n, I have k plus 1. So now I can say that if p1 is true and pk plus 1 is true, whenever p of k is true, then p of n is true for n is all positive integers. Okay, that looks terrible. Okay. Number 7. If z equals cis phi, where phi is acute, determine the modulus and argument of z minus 1. Okay. So z minus 1. Okay, so z minus 1 is equal to r times cis, not r times cis phi, because the modulus of z is 1. So it's equal to cis phi minus 1, which is equal to the cosine of phi plus I sine of phi minus 1. So if we want to group the real parts, it would be cosine of phi minus 1 is the real part, and the imaginary part would be I sine of phi. And then if we wanted to find the modulus of this, we would square this and add them together. So it would be the square root of cosine phi minus 1 squared plus sine squared phi. And that would be, oops. And that's right? Yeah. That is equal to the modulus. And then the argument would be the inverse tangent of sine phi divided by cosine phi minus 1. So that's not a very nice answer. And I was wondering what the book was looking for when it did this problem, so I went back and looked in the back of the book, and they did something a little bit different. This is obviously not an IB problem, it's too vague. So basically, they say that z is an acute angle, or z forms an acute angle, so they drew a picture kind of like this. So this is the vector z, and it says you subtract 1 from vector z, and if you subtract the vector 1 from vector z, it would kind of be adding a vector kind of like that, because the -1 vector goes to the left like that. And both of these lines or vectors are the same length. So you can like form kind of a triangle with these two vectors. And these vectors are form an isosceles triangle. And if this is phi, this is also phi, right? Because two parallel lines cut by a transversal form alternate interior angles congruent. And I'm going to draw another fake line here. Okay. So with these lines, I am going to try to get simpler expressions for the length of this resultant vector and the angle of the resultant vector. So let's try that. So first of all, if this is an isosceles triangle, then, and this angle is phi, then I can already figure out this angle and this angle, right? Each of these angles is going to be, let's say it's alpha. So 2 alpha plus phi is equal to 180 degrees. So alpha equals 180, which is pi minus phi divided by 2. Okay, and how is alpha related to this green angle here? Alpha is related to the green angle because the green angle, which is the resultant vector argument, is equal to phi plus alpha. So what is phi plus alpha? Well, alpha, remember, is pi over 2 minus phi over 2. So if I was to simplify this, I would get phi over 2 plus pi over 2. So it turns out that the argument of the green vector is phi over 2 plus pi over 2. We're going to write that here. Phi over 2 plus pi over 2. And then we're going to look at the length of the green vector. So the length of the green vector is, well, we can figure out half the length of the green vector pretty easily. Do you see the orange triangle I drew? The orange triangle I drew is a right triangle. There's a right angle right there. So I could say that this angle here is half of phi, and this angle here is 90 degrees. And this length here is 1. So I could do sine of phi over 2 is equal to this length here, which we'll call a, divided by 1. And a, if we double a, that would give us the modulus of the green vector. So 2a is equal to 2 times the sine of phi over 2. So let's put that for the modulus. So there's the modulus, and there's the argument. So that was the answer for B. Now for C, they would like to know the conjugate of that. And so basically to find the conjugate, we keep the same modulus, and then we change the angle so that it's negative of what it was. So it would be negative phi over 2 minus pi over 2.